Let me just blow this up a little bit so I can see it a little bit better. Okay, so we had an example there which gave us the prevalence, the sensitivity, the specificity, and the prevalence. So I'm going to make up an imaginary population. I'm going to make a box here. Okay, here's my box. This is going to be disease positive. This is going to be disease negative. This is going to be test positive. This is going to be test negative, just like we would on any of our diagnostic tests. Let me just format this a little bit better. Okay, so I'm going to say that we're going to work with a population of 1,000 people. If the prevalence, as you said, is 3%, then we would expect 30 people out of 1,000, right? 300 would be 10%, 30 is 3%. Out of 1,000, you would expect 30 people to have the disease, and you would expect 970 people to not have the disease. Okay, so now sensitivity. Sensitivity tells us how good we are at predicting that someone has the disease, predicting that someone has the disease given that they have it. And in other words, how good is that positive test? We'll find 98% of the people that have the disease will test positive. That's our sensitivity. Okay, so if I do that, let's see, out of 30, the number of people that test positive out of 30 is going to be equal to 30 times 0.98, right? Comes out to be a fraction. If you're really uncomfortable, we could work this out as if it's a fraction. If you're really uncomfortable with being a fraction, I'm going to change this a little bit. I'll make it out of 10,000 people so that this number is 300 and this number is 970. So we're going to wind 9,700. So we're going to wind up with whole numbers. Okay, same deal. Nothing's changed. I'm just working with a population of 1,000, 3% prevalence. 300 out of 10,000 would have the disease. 9,700 would not have the disease. Well, if we correctly diagnose with our test 294, that means we have six false negatives. In other words, they tested negative, but they have the disease. Same deal now with specificity. That's how good we are at predicting someone doesn't have the disease, right? So we're going to get it right 97% of the time. Here's where we get it right. That's true negatives. Don't have the disease and test negative. So we're going to get, out of these 9,700 people, we're going to get that right 97% of the time, 0.97. And that's going to leave, the difference equals this minus this, or 291 people in that column. Okay, so we correctly predict 294 have it. We incorrectly predict that 290 people that don't have it also. So how many total positive tests do we have? We have 294 plus 291. Okay, 585. How many people don't have it? That's going to be equal to 6 plus our 9,409. Right, and that's going to add up to 10,000. If you want me to do it, I can just approve it to you. Add those together. It's going to add up to 10,000. So now my positive predictive value. What is my positive predictive value? My positive predictive value is the probability that you have the disease if you test positive, right? The probability that you actually have the disease if you've tested positive. Okay, so how many people have tested positive? Okay, so 584 people have tested positive, but only 294 have the disease. So the probability that you have the disease, given that, that's the conditional part, given that you've tested positive, the probability that you have the disease is 294 out of 585. Out of 585 people, roughly about half of them actually had the disease. The other half, 291, did not have the disease. So the positive predictive value is roughly 50%. Let's do the negative predictive value. Okay, the negative predictive value is, given that you've tested negative, what's the probability that you are indeed negative? Well, in this case, 9,415 people tested negative, and of those 9,415, 9,409 of them actually are negative. So negative predictive value is going to be 9,409 divided by 9,415, or pretty much almost pretty close to 100%. That's our positive predictive value. That's our negative predictive value. Okay, so Bayes formula, you can do this directly with a formula that incorporates the use of the sensitivity, the specificity of the test, and the prevalence of the test. But this is kind of a cheat where you can kind of build your own table and do it yourself. So this would work just as well. Okay, so despite the static, does that make sense to everybody? Right? If you go back and look at it carefully, you'll understand how I kind of built this up, from a starting population, the logic that I used here. Okay, so I don't think there's going to be anything that's going to require you to use strictly apply Bayes formula. There will be stuff that's going to ask you to understand what positive predictive value is, what the specificity is, what the sensitivity is, so on and so forth. There might be a question about how the specificity might influence, and so on and so forth. But directly applying from the formula Bayes theorem, not likely to show. I'm making up the test, so I know it's not going to show up. It's not like it's not likely to show up. It's not going to show up on the test. But I still think it's interesting, for an interesting thing and I think when we're done with the test, right now I don't want to go off on a tangent, although I kind of already have. I do want to get to that at some point, so that it's a very elegant way to solve these kinds of problems. So it'll be of some interest. But remind me about that. So after the test, maybe email me later on, or after the test, or remind me on Monday when we're back online. Okay. So I have posted to Blackboard a sample exam. Okay, because I feel a lot of uncertainty out there. So I posted a sample exam. This is not the exam. The exam won't look exactly like this. Some of these questions won't be on the exam at all. Some types of these questions will be on the exam. They might be on a different form, but this gives you kind of a rough idea, and you're going to see things, elements that were in our work in the lab, that were in our homeworks, and so on and so forth, that are coming back up again. So hopefully there's not too much that's a real curveball. There might be one or two things that are not on here that I'll put in that, like, I want to challenge you with, and see how many of you guys really know it, how many of you guys really don't know it. So, but hopefully it'll be fair, and I'll restrain myself from getting too creative. Okay, so let's take a look at this. This document is on Blackboard under course materials. There's a little folder that says exam practice. I'm going to go over this now with you, and I'm going to also pick up some questions on email as I go through this. Things that came up on email. I'm going to go through this, so you can download this document if you want now. Later on tonight, I'll post the answers to this. You can get a look at it now without the answers. We'll go through it, and then later on you'll get a look at it also with the answers. Okay, so first, this should be pretty familiar to you. This is a histogram. This histogram represents the length of stay for patients in a hospital medical care facility. The frequency represents the number of patients, probably up here, and so on and so forth. Randomly selected 20 records of individuals. So how many people are in here? What's the sample size? There's 20 individuals, 20 people. And in fact, you can confirm that. Here's this first bar is 2 people. 4 people stayed for 6 days. 1 person, 2 people, 1 day. So that's 2, 6 total, 8, 10, 12, 14, 16. This is 3, would be 3 people are in here. That's 19 people. And 1 person, unfortunately, stayed in the hospital for 14 days. So we have a sample size of 14. Okay, number one, how many patients stayed at the center for 13 days or fewer? How many patients stayed at the center for 13 days or fewer? Somebody throw out a guess there. 13 days or fewer. Okay, I got a 16. Anybody else? How many patients stayed at the hospital for more than 13 days? One. Oh, yeah, only one person stayed at the hospital for more than 13 days. So that means 19 people stayed for less than 13 days or fewer. Okay? Do you agree with that, Marianne? Does that make sense to you? Okay, one person out of the 20 stayed for 14 days. See, the height of that bar is only one person, right? They're the only ones that stayed for 14 days. Everybody else stayed for 13 or fewer days. Now, if you had counted up from the left, you would have got 2, 2 and 4 is 6, and each one of these is 2. So 6, 8, 10, 12, 14, 16 people. What you did was, if I had changed one word in here, if I had said instead how many patients stayed for fewer than 13 days, you would have been right on the money. See, that's where the issue came up. Right, there you go. Good. Okay, good. I'm glad we all agree on that now. What's the probability of staying in the center for more than 13 days, not including 13 days, exactly 13 days? What's the probability of being here for more than 13 days? Well, as I mentioned, only one person out of 20, right? It's only 1/20th. Exactly. Estimate the median number of days that a stay at the hospital was. The median number of days that a stay at the hospital was. One of the things that you might do to kind of like educate the way that you look at these things is that you can realize if you take a close look, you will realize that. Let me get this thing out. I'm going to hide your comment for just a minute here. Okay. You might realize that, for instance, let me get this back, that each one of these represents a frequency. So in other words, how many people stayed for 5 days? How many people stayed for 6 days? And so on and so forth. So if you can look at it this way, you can look at it as if this were a distribution where we had 2 people stayed for 5 days. Then we had 4 people stayed for 6 days. Then we had nobody stay for 7, but we had 2 people stay for 8. Whoops. Let me get back here. 2 people stayed for 8. 8. Boy, you're giving me a hard time. Oh, there we go. 8. And 2 people stayed for 9. And 2 people stayed for 10. And 2 people stayed for 11. And 2 people stayed for 12. 3 people stayed for 13. And 1 person stayed for 14. Okay, and we got 20 people here, I presume. Okay, so now if I asked you, what is the median value for all of these hospital stays? Well, you would say, well, there's 20 people here. Here, I'm gonna put the patient number here, 1, and I'm gonna copy this down. So series linear 1. Okay, so the person that would be the median value of number of days staying there is going to be half of the 20, right? It's going to be the 10th or the 11th person. Unfortunately, this is an even number of patients. It's 20 patients. So we have 10 lower group of patients and 11 higher group of patients. So in fact, we don't have a middle number. We don't have a single person who represents the median. So what we do is we take the 2 middle values, which are the 9, he's the 10th person, and the 11th, that's the 11th person, and we average these two. So the median number of days in this hospital is 9.5. 9.5 days is the median stay. Now, maybe I'll make sure that it's an odd number on the test so you don't have to wrestle with this too much or get confused by it. If I do it here, I know there's 20 people, so I'm looking for the 10th, right? Two stayed for 5 days. I looked at four stayed for six, so I'm up to 10 people. Two more stayed for 8 days. That's up to eight. Two more stayed for 9 days. I'm up to 10. So now I know, well, I got 10 people that are below nine, and I got 10 people that are 10 or above, right? So it's got to be between these two. So looking at the histogram, I know it's also 9.5. Had there been only 19 people if there wasn't somebody stayed 14, then the middle person would have been the ninth person, and that would have been the median would have been 9. It would have been someone that was in this bar. Okay, so that's the way we deal with that. Let me get comments back here so I can see if you're saying anything to me that I'm missing. Good, you guys are getting the same. Good, you're seeing the same thing I am. Excellent. Okay, so let me move on. Where was I? There we go. Diagnostic test for cancer. Suppose that it was a diagnostic test for cancer was 80% accurate in individuals' cancer. But sensitivity, in other words, 80%, 90% accurate with cancer without cancer, negative result, 90% in healthy individuals. So that's the specificity. Then this test is applied to where there is a prevalence of 1%. If an individual receives a positive test, what is the probability that the patient has cancer? Okay, that's the positive predictive value. Two ways to solve this. And again, the negative predictive value. There's two ways to solve this. One way is to use Bayes' theorem because you have sensitivity, specificity, and the prevalence. The other way is to just build up the chart the way that I built up the chart. However, I'm going to tell you ahead of time that I will give you the pre-assembled chart with the values for positives and negatives and stuff like that, rather than force you to build it from scratch. So you will at least have that table of results. Okay, so but you know now, just like we did before, you know how to calculate the positive predictive value and the negative predictive value. Types of variables. We did it. We did this first homework. We did a lot of this. We almost spent almost the entire first day on types of variables. Which type of variable are these various things? Okay, and I may like kind of leave out discrete and just look for categorical, ordinal, or continuous because there's always it's always so shaky picking one or the other. Okay, school type: categorical, ordinal, discrete, or continuous. Anybody want to hazard a guess? School type: vocational, academic, nursing, and so on and so forth. That's categorical? I agree. Mortality rate due to heart disease: number of deaths per thousand population. Okay, hazard a guess. Now you see what happened here. Number of deaths per thousand population. That could be a number like 3.7 per thousand, right? I would call that continuous. You were assuming that it was going to be a whole number, right? Numerical. Uh, 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 I got a whole bunch of answers there. I would call that a continuous numerical variable. Right? Okay, good. Good. I would call that continuous numerical variable because number of deaths per thousand, I wouldn't assume that it's necessarily 4 per thousand or 11 per thousand, a whole number. It could be, it could be 3.7. It's based on the population could be a million people, and number of deaths per thousand could be a fractional number like 3.5 per thousand or 3.7 per thousand or something like that. So I would call that continuous. I, I would hold discrete only to those kinds of variables that are inevitably only ever going to be whole numbers. For instance, how many siblings do you have? Well, you're not going to have 3.5 sisters, right? You know that's gonna be a whole number, right? So I would only expect you to call it discrete if it's that kind of situation. How many people live in your apartment? How many people are in your apartment right now, right? Well, assuming that nobody has 1 foot in and out the door, and you're going to count them as half, that's discrete. That's a whole number. How many people live in your apartment? Well, you may say, well, 3 people live here, but he only stays part time. I'll try and stay away from something that might be kind of nebulous that you could misinterpret, right? But that's why I don't like discrete, because just because it happens to be a whole number doesn't mean that it's necessarily discrete. Ranking an Olympic event: gold, silver, or bronze. Yeah, ordinal, right? Because we don't know the difference between these. So it could be that the first place guy the second place guy was very close to the gold and the silver. They were like a tenth of a second apart, and third was like 2 seconds behind. But so we don't know the difference between them. All we know is that first is better and second is better than third. So they're ordinal. They have some order to them. Okay. Occupation: a nurse, teacher, etc. Okay. So that would be categorical. It wouldn't be ordinal because you're not going to rate one higher than the other. Of course, if we had said private, corporal, sergeant, lieutenant, that would be ordinal for occupation. If we were talking about rank in the military. Weight in pounds. Anybody want to tell me what weight in pounds is? Continuous. I agree it's continuous. Okay, good. Number of children in a family. How about, yeah, I think that's discrete, right? Okay, we can all accept that as discrete. I'll try and be reasonable about that stuff. Okay, now here's something that we did quite a bit of. We looked at the normal distribution. We looked at it from a couple of perspectives. We looked at it, number one, we looked at it from the perspective of the empirical formula, a rough estimate for the way that normal distributions are distributed. Okay, so I'm going to take a look at this. We have a normal distribution where heart rate is the mean of the heart rate is 80, and the standard deviation is 15. Somewhere here it probably says that it's normally distributed. Here it is, normally distributed. So the mean is 80, and the standard deviation is 15. I'm going to pull up my chart here, and I'm going to draw onto here. And I suggest that you bring some scrap paper with you, and that you consider drawing this stuff when you get a problem like this. Consider drawing it right out. So the middle, the mean, is 80. Okay, and the standard deviation, sigma, is 15. Okay, so the first question we got, whoops, let me get it back here. Let me get this so I can get this back easily. Okay, I can get this back and forth. First question is 68% of this population has a blood pressure between what and what? Okay, let's go over here. 68% of this population has a blood pressure. Well, I know that 68% of a normally distributed population is going to be between one standard deviation below the mean and one standard deviation above the mean. So in this case, it would be 80 minus 15, or 65, to 80 plus 15, or 95, right? So I would put 85 to 95. 95% of this population has blood pressure between, well, that's going to be two standard deviations apart, right? This is going to be 95% of the population. Okay, and that's going to be two standard to be 30 taken from 80, so that's going to be 50, and 30 added to 80, which is going to be 110. Okay, so that's the two questions there. Are we okay? Are we? Did I make a mistake there? 15? I don't think so, right? Okay, everybody okay with that? No good. Yes? Okay, good. Thank you. Had me worried there. I know I make a lot of mistakes. I thought I had that right. Okay. Percentage of this population that has a blood pressure greater than 95. Okay. So I'm looking for a blood pressure greater than 95. 95 sounds familiar. 95 was right here. It was one standard deviation. So the percentage of the blood pressure greater than 95 is this area in here. Anybody want to hazard a guess as to what that area is? Okay, it's going to be 16%. Okay, in other words, this area greater than 95, which is one standard deviation above, is equal to 16%. We know that because one standard deviation below and one standard deviation represents 68% of the distribution. We know the mean is in the middle. So 34% is going to be on here, and 34% is going to be represented here. So, and we know 50% of the distribution is above, 50% is below. So if 50% is above and this part is 34, then the remainder out here above 95 is going to be 16%. Good. Excellent. Okay, so let's go back here. What's the next question? What percentage has blood pressure greater than 80? That should be pretty easy, right? What's 80? 80 is the mean, right? 50%. Good. What percent of the population has a blood pressure above 110? Okay, let's see. Well, 110 turned out to be, let's see, 110 is 30 more than 80. The standard deviation is 15. So that's 2 standard deviations above the mean, right? So 95% of the population is between here and here, right? So what does that leave in this area, little area over here? Okay, anybody want to guess? Right? I would call it actually 2.5%. Based on the empirical formula, you might actually be more accurate at 2.2% if you use the Z table. That's possibly more accurate if you use the Z table. You know, I'm not sure, I didn't do it with the Z table, but with the empirical formula, you'd call it and you see how you got the 2.5%. Because if everything between here and here is 95% of the distribution of the population, well, then you got 5% left. But that tail up here represents what's outside of that range. But there's also a similar one, an identical one, symmetrical one that's down here. It's also out. So that 5% is really distributed 2.5% below 2 standard deviations and 2.5% above 2 standard deviations. 3 standard deviations is 99.7, I think, something like that, roughly 99.7. Okay, so now, last one. What percentage of this population has a blood pressure between 65 and 95? Well, what we're doing here is we're getting a little slick, aren't we? So we're looking between 65, which is 1 standard deviation below. We're looking for between, I wonder if I can change the color here. I think I can. Let me change the color. Okay. Between 65, right, 1 standard deviation below, and 95, which is 2 standard deviations above. I'm looking for the area in here, right? So what do we know that area is? Well, this part over here, right, we know that goes up to 2 standard deviations, is only 2.5% outside, and it's half of 95%. So this area must be 47.5%, right? And how about this area over here? Well, we know that's half of the 68% because it's only 1 standard deviation below. So this is 34%, right? Half of the 68 that it would have been if we had both sides. And we add these two together, 36, 34, and 47.5. And we wind up with 11, carry 1, 81.5%, right? Between 65 and 95. Okay? All right, got a little tricky. Now, keep in mind that we also might get questions. You will get some questions that involve the use of the t-score. Okay, and I'm going to add to this question right here. I'm going to add, okay, let's see. So I can get it to copy. I'm going to add to this one. What percentage of the population has a blood pressure greater than, let's say, 84. 80, let's say, let me think for a second. How about 90? What percentage of the population has a blood pressure greater than 90? And the next one is going to be what percentage of the population has a blood pressure less than 69? Okay? Okay, so greater than 90 first. Greater than 90, if I look at this, right? Well, it's too ugly for me to look at. I have to get a new page here. I can't see what I'm doing anymore. So I'm going to do this page. I'm just going to put the same thing I had on the other one. This is 80. The mean is equal to 80. Standard deviation is equal to uh, 15, right? And I just asked what percentage of this population has a blood pressure greater than 90, right? Well, where's 90? 90 is one standard deviation above is going to be 95. So 90 is short of that. It's in here somewhere. So I want to know what percentage of population is in here above 90. Okay, well, how do I find it? I have to go to my z table. Okay, in order to go to my z table, I need to know the z-score for this value. Well, I can see that it's a positive number because it's the right of the mean, right? Uh, yes, it is. Michelle, what makes you think that 95 is not the one standard deviation above? I'm looking at 90 with the z-score right now. Okay, for because we want I'm looking at a number that we can't use. So you guys get a couple of you guys get ahead of me here. You can't use the empirical formula for. So z, I need to know the z-score. The z-score is the difference between the mean and the value I'm interested in. In other words, z is equal to x minus the mean over the standard deviation is equal to, well, x is 90 minus the mean, which is 80, so it's 10 greater than the mean, over the standard deviation, which is 15, so that's equal to 0.66. That's a positive 0.66 because it's on the right-hand side, right? Okay, so, oh yeah, 65 was minus two, let me think, 95. Did I get that other one wrong? Is Michelle right? Did I screw that up? Did I go one standard 65 and 95? So 80 and 95. Yeah, I did. I should have said 110, right? What I solved was that problem, not the 60. Michelle caught me there. Yes, good. I'm glad you saw that. Okay, but you're right. That what I did was for the value 110. Yeah, I got carried away there because I just assumed that I would do it that way. Okay, in other words, that would be like what I would do to make it a little tricky is make it so that it's not exactly one below and one above, but maybe one below and two above or something like that. But at any rate, okay, so this is that. This is that. So now I need my z table. I'm gonna get my z table like Rusty z table, and I'm gonna go look up a positive 0.66. Okay, positive 0.60123456 is going to be 0.7454, right? That's the area to the left. So this area is 0.745. I'm going to round off for our purposes here. I suggest that you don't round off until the very end. Well, this doesn't say like a bad thing to round off on. So that would leave the area in here is 1 minus 0.745 or 2.255. In other words, 25.5% or 0.255 is the area that's in there. Okay, so now I'm going to go back. The next one said, what percentage of population has a blood pressure less than 69? Okay, well now we're looking at below a certain value. So, okay, where's 69 on here? Well, this is 80. One standard deviation below would be 65. So 69 is inside of that again. Here's 69 in here somewhere, right? So let's see, what's the z-score for 69? The z-score for 69 is going to be equal to 69 minus 80 over 15, the standard deviation. That's equal to 11 minus 11 over 15, right? And 11 over 15 is 11 divided by 15 equals 0.733, right? That's equal to, the z-score is negative 0.733. And it's negative because it's on the left side of the normal distribution. Well, the question was, what percentage of people have a blood pressure below 69? So it's this area in here. So we're going to go to our Z table again. Okay, if I can get to it back here, buried back here somewhere. I'll do it this way. Come up again. There it is. Okay, negative 0.733, negative 0.70123. Okay, so that's the closest I can get. It's closer to this than 7.4. So I'm going to go with this one over here, 7.3, which is 23 point. I'm going to call it 23.3. 23.3. So this area in here is 0.23.3 or 0.233 is this area in here. Now, if I asked you what percentage of this population it has a blood pressure above not above 90 or below 69, what would you tell me? What percentage of the population had a blood pressure above 30 or below 69? Somebody hazard a guess. You got everything you need to solve this right here. You just give me the numbers to add together, and that'd be good enough. You don't have to tell me the actual final answer. What percentage of this population has a? Okay, yeah, you just add those. Oh, hang on, I got a little bit of a problem there, Alexa. Right, the percentage of the population that's above 90 is 25.5%. The percentage of the population that's below 69 is 23.3%. So the percentage that's above that 90 or below 69 is the sum of 23.3 and 25.5 added together. What percentage of the population, one more question, what percentage of the population has a blood pressure between 69 and 90? Okay, what percentage of the population has a blood pressure between 69 and 90? Okay, it's going to be 1 minus those two areas that are on the outside of it that I just, exactly right, Michelle. Good work. Okay, so I think I beat that to death. Let's move on to something else. Okay, but there's bound to be stuff like that on there, so we want to practice that a little bit. In one region, let me save this. I remember to put those answers in there later. Okay, in one region, now this is a little bit tricky, this question here, but it has stuff in it that's elements of what we just were doing last night. In one region, the December energy consumption levels for single-family homes had a mean of 1,500 kilowatt hours and a standard deviation of 200. Assume that that the consumption levels are normally distributed. Okay, if a neighborhood consists of 100 houses each, and if we consider that the neighborhood to be a random sample for the region, what is the mean number of kilowatt hours and the standard deviation of power consumption of all neighborhoods? Okay, well, they just told us, didn't they? In other words, well, they just told us that the mean for all the neighborhoods was 1,500. So now this is a little bit tricky the way that this is worded. I'm hoping that it won't be quite as tricky as this tomorrow. But what they're saying here is the whole entire area, let's say state, has a mean of 1,500 kilowatt usage with a standard deviation of 200. If you looked at individual neighborhoods that consist of 100 houses. In other words, the sample size is 100 houses. If we consider each neighborhood to be a random sample from the region, what is the mean and standard deviation of power consumption for neighborhoods, not for the whole region, but for neighborhoods? Well, anybody want to hazard a guess on what the mean would be for the neighborhoods for each if we took the means of all 100 neighborhoods? Anybody want to hazard what a guess would be? It's the same thing as if we took repeated samples from a population, as we said yesterday. The mean of the samples is going to approximate the mean of the population. Perfect, 1,500. Thank you very much, Nicole. Okay, but the standard deviation of those repeated samples of size 100, standard deviation is going to be different. The standard deviation is going to be related to that 200, but it's going to be equal to the standard deviation of the population, which is 200, but it's going to be divided by something. What's it going to be divided by? Okay, it's going to be divided by the square root of the sample size. The sample size was, I'm going to put square root, and the sample size was 100. Square root of 100 is 10. So the standard deviation is equal to 20 for the individual neighborhoods, for the neighborhoods as a whole. Okay, so a little tricky, right? But now let's look at some of the questions. What's the probability that the power consumption of a individual home, just one home, not a neighborhood, 100 homes, but of any home out of this group of all these homes in this state exceeded 1,700 kilowatts for the month? Okay, well, I would have a normal distribution. The mean would be 1,500. The standard deviation would be 200 because I'm looking at individual homes in this population. So I would say, well, that's 1.5 standard deviations below the 1,500, right? Because it's 300 below 1,500. Standard deviation is 200. That's 1.5 standard deviations. Excuse me. Uh, I, I, let me start again. I got that wrong. 1,700 kilowatt hours is one standard deviation, 200 above the average for the entire region. So it's one standard deviation above. So what's the probability that the power consumption of individual home exceeded being one standard deviation above? Is higher than one standard deviation above? Well, we know from the empirical formula and what we just did before that that's going to be roughly 16%. If you use the z-score is equal to 1, and find what's below it and subtract it from 1, that'll give you even a more precise answer than 16%. Okay? Now, let's look at this from a different perspective. What's the probability that the average power consumption of a neighborhood of 100 houses exceeded 1,700 kilowatts for the month? That's a different problem. Now, since we're looking at a sample distribution, we don't use the population standard deviation. We use the same mean, right? The mean still is 1,500, so this is 200 above the mean, right? But we use the standard deviation for the sample distribution, right? So in this case, it's going to be 20. So it's going to be 200 divided by 20, or a z-score of 10, and that's going to be just a ridiculously high number, right? It's going to be way, way, way tiny amount of the probability that they'd be higher than 1,700, that a neighborhood would be higher than 1,700 is basically almost zero. Okay? Okay, so, but I'll try and get it so that there's a little bit clearer delineation between when you're working with a sample and a population. But you see what happened there. Okay, identify the following studies of experimental or observational. The health and life habits of a group of 160,000 nurses are followed over a period of several decades. Is it experimental or observational? It's underlined observational here because I think it's a typing thing in Excel. Let me get rid of that. I'll get rid of that. Okay, go ahead. Is it observational? It's observational, right? Because you're not doing an experiment, you're just observing them. Cancer patients entering a clinic are provided standard treatment, which involves surgery and only sometimes involves surgery plus chemotherapy, depending on stage of the tumor. Researchers track a group of patients for a period of years to find out whether those who received chemotherapy had a different survival rate than those who received surgery only. Is this experimental or observational? This is tricky. Well, I guess it's not so tricky. It's observational because it would have been experimental if you randomly selected the patients and chose you get surgery only, you get surgery and chemotherapy, and you split them up randomly into groups. That would have been experimental. But this is you're just observing what happened based on their treatment. Okay. I'm going to go down this one. Identically designed political poll is conducted in 10 poor neighborhoods and 10 wealthy neighborhoods to determine, that's observational. Hey, let's look at this one. Cancer patients are entering a clinic randomly assigned to receive surgery. Well, I just said that, didn't I? Didn't I just describe this? Surgery plus an experimental. Then you know already that that's experimental because that's the one I just described. Okay, let's move on. Now, this came up as about somebody emailed me about this. I won't say who, but somebody emailed me about this. Binomial distribution. I know they're not the only ones having problems with this. So let's take a close look at this. Okay. In any given year, 1 in 3 Americans over 65 will experience a fall. So the probability of experiencing a fall is 0.33, 1/3, right? 1/3 of Americans. If you have 4 living grandparents over the age of 65, assuming the probabilities for each grandparent are independent, what is the probability that none of the 4 grandparents will experience a fall? They want the answer is decimal place. Okay, that's a binomial distribution, right? It's a binomial distribution because they can either fall or not fall, right? So what do we have here? The number of successes, okay, the number of successes is 0. We want to know what's the probability that none of them will have a fall. So successes is 0. The number of the sample size is 4. Your sample is your 4 living grandparents, and the probability is 0.33. Now I'm going to open up. There is a table in the back of Agresti that you can use to do this. However, I personally think the table's nuts. I think it's hard to interpret that table. So I'm going to say probability, binomial, and parentheses, binom dist, I should have put, binom dist, parentheses, okay, is equals binom dist. It comes up with the suggestions. First, the number of successes. Number of successes again was what? 0. Number of the sample size, right? Or trials, the same thing as sample size, was 4, comma. And the number of, yes, that's right, sample size is 4, not the successes. And the probability is 0.33. I'll add another 3 because it was, the third, really, comma. And now, do I put in false or cumulative? I'm going to wait for an answer on this. Do I put in false or cumulative? Somebody make a suggestion here. False or cumulative? I got a false because that's good thinking because it'll only give me the probability for exactly 0, which is what they're asking. But you want to know something? If I put in false and hit enter, I get the probability for exactly 0. And if I had put in true instead, I get the same answer because there is nothing below 0. So cumulative and not cumulative for that number is the same, since that's the lowest number you can get anyway, right? But if it were more than 0, if we were talking about 1 out of 4, 1 out of 4, 2 out of 4, 3 out of 4, then we would have to make a real decision about cumulative or not cumulative. Next question: what's the probability What's the probability that 1 or more grandparents will experience a fall? Okay. Well, we know what the probability is that no grandparents are going to experience a fall. What's the probability? That's 0. What's the probability that 1 or more will experience a fall? Okay, that's right. 1 minus, that's all the other possibilities. 1 minus the probability that nobody's going to experience a fall. Whoops, I didn't put an equal sign in there. Okay, equals that. Yeah, so it's 80% roughly. Okay, so now what's the probability that 2 or fewer grandparents would experience a fall? 2 or fewer equals binom dist, parentheses, 2, let me hit escape here, 2 or fewer equals binom dist, parentheses, probability that 2 or fewer. Okay, what do I put here now for a number of successes? 2 or fewer. 2, good. Trial stays the same. 4, 0.33 stays the same. And do I put true or false in here? True, because I want it to include 2 or fewer, everybody below that. So that's, and if I were to say 3 or more, right, then I would just say 3 or more. I would just say 1 minus 2 or fewer. That would be, oops, keep forgetting to put the equal sign in there. I would put in 1 minus that. That's the remaining probability. Now, a little bit of a curve. How about fewer than 2? Equals binom this, parentheses. What do I put in here? What should I put in there for number of successes for the statement fewer than 2? 1. Exactly right. Because I want fewer than 2. I don't want to include 2. I just want to include 1 and 0. 4, comma, 0.33, comma, and that would be true because I want the 2 lower number. I want everything below 2, but I want to include 2. How about how about more than 1? How would I say more than 1? What should I solve for first for more than 1? Well, I would solve for 1 and everything below it and then subtract from 1 because I want everything. I don't want to include 1. If I solve for binom dis equals 1, comma, the cumulative, I get 1 and 0. And then if I subtract that from 1, that leaves me for everything that's above 1. In other words, more than 1. Okay, so I think that we beat that to death. Okay, let's move on. Okay, below our data from a randomized trial designed to evaluate the effectiveness of new pain reliever. Blah, blah, blah. Trial currently used standard care. So we got a new pain reliever and a standard pain reliever. We have a study. 50 people took the new one. 50 people took the standard one. 34 people experienced a reduction in pain, and 66 didn't experience a reduction in pain. What's the probability of experiencing a reduction in pain given that, conditional probability, the patient received the new pain reliever? Okay, so it's a fraction, right? So what's the fraction going to be? Probability you had a reduction in pain given that you received the new pain reliever. How many people received the new pain reliever? 50 people received a new pain reliever. How many of them had a reduction in pain? 23 out of the 50. So what's the probability? It's 23 over 50 or 46%, 0.46, right? Only since the condition was that they have taken a new pain reliever, that's our condition. The conditional probability is 23 out of the 50 that took that. I'm ignoring the ones that took the other because they're not included in that condition. Okay, let's read the next one. What is the probability of experiencing no clinical meaningful reduction in pain given that the patient received the new pain reliever? Again, all we're looking at is the people that received the new pain reliever, right? And what's the probability they had no meaningful reduction? 27 out of the 50 had no meaningful reduction. That's 34%. Excuse me, 54% of the population had no, or 0.54 of the new people that got the new one. So it's 0.54. Okay, are you guys comfortable? I see Salita put the answer in. I know that there's a lag here. Even in my voice, probably there's a bit of a lag. So I wind up waiting a little bit for the answers, and I'm not sure if you're hesitating or if it's just part of the lag, that's a natural lag of a second or two or three that's built into this. So sometimes you may see me go on when you think I'm still waiting for you to do something. Okay, probably know that, but descriptive statistics, this is the last thing I want to mention, is that it's likely that I'll ask you to do a calculation, basic statistical calculation, mean, median, percentiles, so on and so forth, standard deviation, so on and so forth, using Excel and or SPSS. Okay, so I'm gonna, and it will be no more complicated than what you did on homework number 1 and 1A. Okay, so if you're able to do what was on homework 1 and 1A,
it's 9 o'clock.
You should have no problem with this. The computer's talking to me there. Okay, you should have no problem with that. Okay, any questions? Okay, this is up on Blackboard now. You can download this. I'll post the answers within about an hour or two. Hang on a second. Let me just save that so I save the changes that I made on it. Okay, let's see what questions I get here. Can you explain the rationale for using true or false in the binomial? Okay, I'll do it again. Let's see. Equals binomial. I'm gonna give you a situation. You have a population of people. That's a good population, right? People is good. Population with a 10% rate prevalence of diabetes. Okay, I can't see that behind my window over here, so you can see it, I think. Okay, there you go. 10% prevalence of diabetes. You sample, randomly sample, let me change that, randomly sample 10 people, 12 people from that population. What's the probability that exactly 3 people have diabetes? Well, if I told you that I sampled 3 people and all 3 of them had diabetes, we know that that probability is kind of like flipping a coin, like a coin flip. The chances of getting 3 heads is zero point 0.5 times 0.5 times 0.5. Probability of getting 3 people in a row that you sample that have diabetes is zero point 0.1 times zero point 0.1 times zero point 0.1. However, that's not what we're asking here. What we're asking here is that given that we're going to sample 10 people, what's the probability that exactly 3 of them have diabetes? Well, there's many possibilities on how that could work out. It could be out of the 12 people, the first person, no, no, yes, no, 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 yes, no, no, yes, no, no, no. Or it could be yes, yes, no, 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 yes, no, 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 and so on and so forth. There's a million ways that you could have 3 people out of 12 that have diabetes from this population. So, but the thing that these possibilities all have in common is they have 2 possible outcomes: have diabetes or don't have diabetes. 2 possible outcomes is binomial outcome. Okay, so I'm going to do a calculation now. Equals now we can calculate this probability using a function in Excel or table at the back of the book, which says binom distribution or binom dist. When I hit parentheses, the open parentheses, Excel helps me out with this problem. Okay, it tells me it wants to know the number of successes. The number of successes is the number of people that you chose randomly that meet your criteria. In this case, success is have diabetes. That would be 3 people. Comma. The number of trials is the number of people you sampled. That would be 12 people. The probability would be the prevalence of diabetes, the chance of any individual having diabetes, 0.1. Comma. And then we have to fill in cumulative, false or true. We have to put in for cumulative. If I put in false for cumulative, it will give me the probability for having exactly 3 people out of 10 that have diabetes, and that probability is 8%. If I had put in, if I had put in true, I'm going to do the same thing: 3, comma 12, point 0.1, comma. Oh, I left the comma out there. 12, comma 0.1, comma. Except this time said true. It's going to give me the probability of having 3 out of 12, 2 out of 12, 1 out of 12, or no people out of 12. In other words, all the possibilities of having 3 or fewer people that have diabetes out of a randomly selected group of 12 people. And that's going to be 97%. Like unlikely. In other words, another way of looking at that is it's only about 3% chance that I will have 4 or more people, right? Because this is the chances of having 3 or fewer. So 1 minus that would be the chances of having 4 or more. Okay, hope that helps a little bit. Would we have to do any fills downs, or is it optional? It's not that hard to do fill downs. However,